Hi, my name is Kevin Rogers, and I'm going to be talking to you today about circuits. This tutorial should give you a basic understanding of electronics engineering and how to build some useful circuits in conjunction with Arduino. So this is our roadmap for this talk. We're going to start off with the basics of electricity as well as properties, and we'll move in there to some of the common electrical components that we'll use in the circuits. From there we'll actually do circuit analysis and learn strategies for solving them, and wrap it up with some real-world examples. So electricity is the movement of charged particles. It's comprised of voltage and current. Voltage, or electric potential, is the amount of work needed to move one unit of charge between 2 points. It's a relative measurement, and its typical reference point is ground or 0 volts. On the other hand, current is the amount of charge to be moved. So a great metaphor for electricity is a waterfall, where the height of the water falling is voltage and the amount of water falling over the cliff is current. Additionally, electricity can be either alternating current or direct current. For today, we're only going to be concerned with direct current. Also, an important property is that electricity always flows from voltage high to voltage low. So going back to the waterfall, you would never see water going from bottom back to the top. Electricity performs the same way. Also, electricity more properly takes the path of least resistance. So imagine water, say, in like a pipe, and that pipe splits into 2 different outlets, with one outlet being fatter than the other, allowing more water flow. The final note here is that volts jolt and mils kill, and that's more of a safety thing. When we're talking about electricity, it's important to mention, being safe and treating these things with a certain amount of respect. People can take tens of thousands of volts and be perfectly fine. That's what that volts jolt means. Mils kill means that it really only takes 100 milliamps to stop your heart. And to put that in perspective, your house, has 20 amp outlets in it. That's enough current to kill you 200 times over. So, though a typical Arduino doesn't get anywhere near those levels, it can max output 40 milliamps on 1 pin line. And while that isn't enough to, cause, death, that is enough to cause burns or mild electrocution. However, you are perfectly safe working on Arduinos, being that it's digital signals, so the voltage output's only 5 volts. Because the voltage is so low, there's not enough voltage to push that through any significant part of your body. Still, it's a good idea to treat this with a modicum of respect, hence the phrase. There are many types of different electrical components. For the purposes of this presentation, we are going to focus on these ones. First up is the resistor, probably the most fundamental common component in all electronics. Resistors provide constant resistance in whatever circuit they are in, and they don't have a specific polarity, so they can be put in either direction. Batteries are another really common component. They provide constant voltage in their circuits, and hence are sometimes called constant voltage sources. They do have a specific polarity, hence it does matter in what direction you put them in. That's why when you stick AA batteries in a remote, you have to make sure to line up the positive and negative terminals. Followed by that are capacitors. Capacitors are a temporary store of energy. Typically, a capacitor will be charged up by some kind of battery in a circuit. The capacitor will then reach the same voltage as the battery. Once the battery is disconnected, then the capacitor will quickly dump that energy. So capacitors are rated in terms on their speed of charge and discharge by a measurement known as capacitance. And applications such as making tasers or defibrillators, things that need quick energy delivery, you'll see capacitors. Finally is diodes. Diodes are a really more modern component, but they're extremely important to modern electronics. Now, diodes themselves aren't necessarily used in every application they were before. but the technology to make diodes is what is primarily used to make integrated circuits in CMOS technology. So the benefit of diodes is that they're one-way valves. They essentially only allow current flow in one direction. Hence, they do have a polarity, so it doesn't matter what direction you put in it. Diodes also always provide a constant voltage drop across them, which will be important when we're doing circuits in a second. And if you look here over on the right, here are some of the common components associated with it. So on the top left is a common resistor, followed by AA battery. I think we all know that one. Capacitor, there can be ceramic or ferritic capacitors. This is a ferritic capacitor, which is typically a capacitor used for higher stores of energy. Ceramic capacitors tend to store less energy, but are much quicker at charging and discharging. And then finally, on the bottom right is a LED, a light-emitting diode. So moving on to those components in circuits, we need to talk about the fundamental rules for circuit analysis. Firstly, when analyzing circuits, we assume all perfect conductors and power sources where there's no loss or inefficiency in the components. So if you look at the circuit here on the right, first off, these straight lines are just wires connecting the components. And we have a voltage source, so a battery, connected to some resistor. So between this battery and resistor, there's no drop in voltage, and the battery will always put out exactly 5 volts. Moving on, Ohm's law is a fundamental law of electricity, and we use it in solving circuits, where we relate voltage to current and resistance, hence getting V equals IR. From that, we can actually do a brief demo to prove that. So here, going back to my circuit, I want to determine what the current is, current I1 in this circuit. So I can do that by taking my voltage here, 5 volts, equals my current times resistance. Okay, so if I take 5 volts divided by 100 ohms, I'll show that I1, my current, is equal to 50 milliamps. Notice as well that with if there is no loss in the conductor up to the resistor, that means that there's 5 volts here above the resistor and 0 volts beneath it. Hence, 5 volts must be dissipated by this resistor. Okay? So if that's true, that means the current flowing through the resistor is in the same direction as I1. Hence, the polarity, the induced polarity in R1 is from positive on top and negative on bottom. So you may have already heard me mention the term polarity. Polarity is current is the direction of current flow relative to the circuit. And some components do have an inherent polarity that they need to be placed in the proper direction. Other components like resistors really don't have a polarity and just kind of go with whatever ends up happening in the circuit, which is what we see here. When analyzing circuits, there are a few rules that will help us. First up is Kirchhoff's voltage law, also known as KVL. Basically, for any closed loop series path, the sum of all voltages will be 0. So what that means is if you look at the right, this is maybe like a small mock-up of like a circuit. Anytime you have a closed loop, the net sum of all the voltages in that closed loop will be 0 volts. So you look here, this little loop is 0 volts, this little loop is 0 volts, but also notice that the outer loop is also 0 volts. Basically, as long as you can go from one solid path without going back over yourself, draw a path all the way around and come back to your origin, you have what is a loop. Next up is Kirchhoff's current law, or KCL. This law is actually kind of the same coin as KVL, but said in a different way. And KCL says that the sum of all currents entering a node is equal to the sum of all currents leaving it. And once again, if you look to the right, here's a mock-up. So imagine, if you will, we have a blown-up section of this circuit right here, down here, and we have current flowing into the node. Well, the current leaving that same node must be, the sum of that current must be the same. I1 must equal I2 plus I3, assuming that I1 flows into the node and I3 and I2 both flow out. So both these rules kind of work together to give us this summary, series versus parallel circuits. So in parallel circuits, each branch has the same voltage, right? So right up here, if you look, we have a node here and a node here. So from the perspective of here, and if we're, going to go have current going down and out, down and to the right, this line here is in parallel with this line here because they both start and end at the same location. That's the definition of parallelity, a parallel circuit. Also, a series circuit has the same current. So, once again, if you're looking at this circuit here, right, this line here, let's say there's more than one component on this line. Maybe you have two resistors. Well, because these resistors are in series with each other on the same line, they have the same current going through them, right? So current is constant. So what we'll end up using is Ohm's law in conjunction with KVL and KCL to solve our circuits. And I'll show you that in our example. So here's our example. In the prompt, we are using a 1.6 volt by 10 milliamp LED. Design a discrete circuit for an Arduino so that when pin X is set high, it illuminates. So this is a very common task. When you activate a pin or receive a signal, it's typical to have an indicator LED to give status. The LED we were supposed to use has a set activation of 1.6 volts. So in whatever circuit it is in, that will be the voltage drop across it. Additionally, the LED has an optimal current of 10 milliamps. So any more than that, we risk blowing it out while too little won't turn it on. Arduinos output 5 volts when a pin is set to high, so we can simulate our circuit with a 5 volt constant voltage source. If we were to hook up the circuit like this, with just the LED running to our pin X, it would work. But it would also stop working pretty quickly due to too much current. So we're going to have to add a component in there, and we're going to add a 1k ohm or 1000 ohm resistor to limit the current. So we've added it, but now we have a new problem. The resistor is limiting the current too much. The LED won't turn on now. So let's go ahead and apply some circuit analysis and try to figure out an appropriate value to drive 10 milliamps in this circuit. So I went ahead and added our equations to the top right. Typically when doing circuits like this, there are a lot of different approaches, but we'll typically just start with what we're given and kind of work outwards from there. So starting off, we know that from KCL that because there are no branches or nodes in this circuit, that the current is the same through all components, right? So we know we need to get 10 milliamps in the LED. Hence, there's 10 milliamps traveling through pin X as well as through resistor 1. Also, due to KVL, we also know that the net voltage in the loop must add up to 0. So we have one voltage source here, pin X, that's supplying 5 volts. Hence, the voltage in R1 LED must add up to be 5 volts as well. So we can use this. We can use KVL to write an equation. So 5 volts equals voltage R1 plus voltage LED. Now going back to our given, we know that the LED has a constant voltage dissipation of 1.6 volts. So we can add that in, and 5 volts now equals voltage R1 plus 1.6 volts. And that ends up giving us voltage R1 equals 3.4 volts. So now we know that in this circuit, 3.4 volts are dissipated across R1. Well, to get our final current, all we need to do is write Ohm's law down, right? This one up here. So voltage, 3.4 volts, equals current, our 10 milliamps, times resistor in resistor 1, right? So when we rewrite this and solve for resistor 1, we finally get 340 ohms. So that means 340 ohms is the optimal resistance to put in here, okay, to drive exactly 10 milliamps in our circuit. So that's going to wrap up this presentation. What you should take away from this presentation. If you really want to get good at doing these kind of things, really the things you got to get down are Ohm's law and application of KVL and KCL. The fundamental rules are basically what all these circuits are built off of. Yes, you'll see new components, but you know every component has its own eccentricity, but they still are based off KVL and KCL. The benefits to doing this, you know, really in future employment of software people, and this is really who that is geared towards software people trying to learn hardware, is it really helps you get up and running with faster troubleshooting. If you're dealing with hardware on a daily basis, you know, if you can really take a look and when you have a problem and really understand if the problem is coming from you writing bad code or you having bad hardware, it's going to save you a lot of time. Also, I can't describe to you how many times you're going to deal with in your life as a software person, debates with your hardware team saying that you effed up. And it really can help iron things out and save you a lot of time, hassle, and stress if you understand this to a degree to be able to go tell your hardware team that, no, you're wrong. Thank you. Have a good one.